So in this video, let us discuss the another type of simple harmonic motion, that is motions executed by spring, mass subjected to spring. So let me call this as vertical vibrations, or mechanical vibrations. So this is also a kind of simple harmonic motion where the vibrations are due to suspended spring. Say I have a spring whose one end is free or have attached a load. So let me mark this point as my equilibrium position P. So when I attach load of mass M, so we all know that naturally the spring expands. So this is the expanded spring under the action of load M. So the point P has come here. So when I remove the load, we know that the spring compresses, expands gradually until it comes to its equilibrium position. So this is the point the point P when the spring is compressed. So let us compare the diagram. So this is the equilibrium position. When the spring expanded, it moved a distance of say x1 from its equilibrium position. So this dotted line is the equilibrium position. And when the spring compressed, it compressed by a distance of x2 from the equilibrium position. So how do I say this is a simple harmonic motion? Whether the spring expands or contracts, there exists a restoring force. How is a restoring force? In this case of expansion, the restoring force, say F1, acts in this direction because this F1 tries to bring the spring to its equilibrium position. When the spring contracts, there is a restoring force acting on the spring in the downward direction so that the spring expands and comes to this equilibrium position. And hence, I can say, depending on whether the spring is expanding or contracting, there is a constant restoring force acting on the spring, which is trying to bring the spring to its equilibrium position. So I can say the restoring force is proportional to the distance x. So the restoring force depends on what is the value of x. Less x value, that means less is the compression or expansion, lesser is the force required to bring it back to the equilibrium position. Okay, or equilibrium position, okay, I should have written here, equilibrium position is opposite to the direction of displacement, or magnitude of the restoring force is equal to the displacement. The restoring force is proportional but opposite to the direction of displacement, or the magnitude of restoring force is equal to displacement. So when I remove the proportionality sign, I have to replace by a constant. So let me say the constant is K, where K is called spring constant or stiffness factor. K is called spring constant or stiffness factor. So what is K? K is defined as a ratio of F by X. That means, say if I have a unit displacement from the equilibrium position, say 1 centimeter or 1 meter or whatever, to the applied force. So this ratio gives us spring constant. So I can say under the action of unit force, if the spring undergoes a unit extension, it could be compression also. K is defined as F by X. So the unit of stiffness factor is Newton per meter. Now this stiffness factor or spring constant naturally tells us how stiff the spring is or how strong the spring is. Let us understand this by comparing two springs. Say I have a spring S1 and I have another spring S2. S1, let it have a spring constant K1 is equal to say 20 Newton per meter. And for the spring S2, let K2 be equal to 60 Newton per meter. On comparison, it is obvious that K2 is more than K1, or K2, that is the spring S2, is more stronger than spring S1. Why? Because there is lot of difference in their stiffness factors. Higher the stiffness factor, stronger is the spring, because higher the stiffness factor indicates that the spring can withstand more load without breaking, and hence higher the stiffness factor or spring constant, stronger is the spring. Now, in this section of simple harmonic motion, once we are aware of what is stiffness factor, we'll be discussing uh, springs in series combination and parallel combination. So, what does that mean? Suppose I have two springs S1 and S2 attached to mass m. So instead of replace, and I can replace S1 and S2 by an equivalent spring whose spring constant is say Ks. So if S1 has a spring constant K1 and S2 has a spring constant K2, I can replace S1 and S2 by a single spring S whose spring constant is Ks, where Ks is given by K1 K2 by K1 plus K2. This is like the capacitors in series combination. So instead of, suppose we come across a problem where we have to deal with many springs, connected in series and parallel combination, we can always find an effective spring constant. We can replace the n number of springs by an equivalent spring. Also, we'll be doing another derivation similar to this kind when springs are connected in parallel combination. Suppose we have to deal with the problem where 3-4 springs are connected in parallel, we can replace them by a single spring. So in this case, let me consider two springs S1 and S2, both of them attached to a common load, say M. So I can replace S1 and S2 by a single spring S whose spring constant is Kp, where Kp is equal to K1 plus K2. So we'll be doing these two derivations in this section. Thank you.